Hello and welcome back to Discrete Mathematics. This week we're going to be looking at methods of proof. So we're going to cover the three sort of major methods of proof. One are going to be direct proofs, which are kind of the most straightforward. And then we're going to look at proofs of contraposition, which is a method where you try to prove the contrapositive of a statement rather than the statement itself. And then proofs of contradiction, where you try to negate the statement and then try to show a contradiction, that the negation is not true, therefore the original statement must be true. We'll get into it as we go. Here's the idea. That for most problems, you can't do something as simple as what we did earlier, where you have those sort of two-column proofs where you sort of have every single statement and then every single little rule, because there are so many rules that stating some of that stuff is just, how would you go back through all of high school algebra and geometry and try to figure out all the different rules for, why I'm able to multiply both sides of an equation by, well, actually, I know that rule, but you know what I'm saying. Things get complicated. And so most mathematicians will actually write their proofs in paragraph form, right? They will explain what they're doing and perhaps not leave some stuff out, right? Like you could prove it, but like they don't need to because it's understood, as opposed to having to state everything for every single transformation that you make. So there's a couple different ways of proving things, right? The first is going to be a direct proof. Now, this is actually very similar to what we did before with our two-column proofs, right? We started with a statement, right? Here's an implication. Thing A implies thing B. Or in this case, we have thing A implies thing C, right? Because we're going to have these middle steps, right? And so what I do is I start with A, and then I make a statement from A using some sort of axiom or rule or other thing that we've proven. And then I go to another statement, to another statement, to another statement, to another statement until I eventually get to the thing I'm trying to prove. It's a direct proof. You can sort of see the sort of linear pattern of stuff. And so let's look at an example. So here's the claim we're trying to prove. For all real numbers x, if x is greater than 1, then x squared is greater than 1. All right. So here's the proof. We are going to assume the first thing, right? So let x be a real number and suppose that x is greater than 1, right? We're assuming the thing on the left, the thing after the if, I guess. And then we're going to multiply. You can multiply both sides of the inequality by a positive number. That preserves the inequality. So then you can multiply both sides by x, and that will give you x squared is greater than x. Well, if x squared is greater than x and x is greater than 1, then you know that x squared is greater than x is greater than 1, or if you simplify it, x squared is greater than 1, which is exactly the thing you were trying to prove, right? Done. QED. You've proven this. And so then that's sort of your rule of thumb for things when you're trying to do a direct proof. For any statement, for all x, p of x implies q of x, we have that sort of implication. You're going to want to write a sentence that sort of looks like, let x be element of the domain. In this case, let x be a real number. Let x be a positive integer. Let x be a whatever, population of things you're talking about. And then suppose p of x, the thing to the left of the implication. In this case, we're saying if x is greater than 1, then x squared is greater than 1. So x is greater than 1 is p of x. So we're going to say, let x be a real number and suppose that x is greater than 1, which is exactly what we did. And then we work through a series of rules and axioms until we get to the thing we're trying to prove, direct proof. Now, sometimes that proves to be pretty hard, right? And so you can't really get from A to B directly. So then what you might want to try to do is, instead of proving it directly, instead, try to prove something that is logically equivalent. In this case, the contrapositive. And we would call that a proof by contraposition. If I can prove the contrapositive of something true, then I'm effectively proving the original statement to be true because they're logically equivalent. So, in case you forgot, the contrapositive of a statement, P implies Q, is not Q implies not P. Right? You sort of switch the direction of the implication and negate both sides. And the contrapositive is always true, right? We gave the example last time of if you set your alarm, then you will wake up on time, which also means if you did not wake up on time, then you did not set your alarm, because if you set your alarm, you would have woken up on time, right? So Contrapositive is an equivalent statement, so therefore, if I can prove it true, then we can prove the original statement true. Your rule of thumb here is then, if you have something in the form of for all x, p of x implies q of x, you want to begin your proof with a sentence like this. Let x be an element of the domain, and suppose not q of x. That's where you're starting, right? Because the contrapositive goes the other way. Not q of x implies not p of x. So we're going to assume not q of x, and we are going to work to try to prove not p of x. Make sense? So here is an example. So suppose x and y are positive real numbers such that the geometric mean, which is x times y square root, is different from the arithmetic mean. Add them together, divide by 2, right? So if that's true, if the geometric mean is different than the arithmetic mean, then x does not equal y. So instead of trying to prove this sort of directly, we're going to prove this the opposite way. Really what this is saying is, suppose you have an x and y, the sort of radical xy not being equal to x plus y divided by 2 implies x is not equal to y. So what we're going to want to do is flip it, right? I'm going to assume x does equal y, and then I'm going to try to prove that if x equals y, then the arithmetic mean and the geometric mean are the same, right? Not that they're different. So if these two things are different, that implies x is not equal to y. So what I'm going to do is flip it and say x is equal to y, and I'm going to prove that these two things are the same. All right? So if that's the case, let x and y be positive real numbers. The domain is still the same. And suppose x equals y. Then we can say that the radical, or the square root of xy is just equal to the square root of x squared, because x is equal to y. If that's the case, the square root of x squared is just x, because x is positive. We said that it had to be a positive real number. If this is the case, then x is equal to x plus x divided by 2, because math. And then finally, if x plus x divided by 2 is equal to x plus y divided by 2, because x is equal to y. Therefore, the geometric mean and the arithmetic mean are the same. The square root of xy is the same as x plus y divided by 2. I've proven the contrapositive, and that means I've actually proven the original statement. If the arithmetic mean and the geometric mean are different, then x does not equal y. Make sense? Kind of weird because in the claim, everything was negative. So when we took the negation, we actually are proving the positive side. Then, the last one we're going to talk about today is proof of contradiction. So proof of contradiction basically means that two statements, A and not A, cannot both be true, right? If A is true, then not A is false. If A is false, then not A is true. And so what we can do then is, instead of trying to prove something true, we could try to find a contradiction. We could try to find something that we know, a statement that is always false. If we can essentially negate the statement that we're trying to prove, and then show that that leads to something that is always false, then we actually are proving the original statement, right? So in this case, our rule of thumb is to prove a statement A by contradiction, you just start with the following sentence. Suppose to the contrary that not A. Then argue as you would in a direct proof until you reach something that is always going to be false. There's a pretty famous example of this one. But this one's going to require a lemma. So remember, a lemma is just something that we would have to prove along the way, and then use that as part of our larger proof for the thing we're trying to do. I'm going to skip that proving of the lemma just because it's kind of basic math and you probably know it already, but it's required for this proof. So that's just to say that let n be an integer. If n squared is even, then n is even. In other words, if you take any even number and you multiply it by itself, it's going to be even. The only time n squared could ever be odd is when n is odd, right? So if n squared is even, you know that n is even. And you know that kind of from high school, right? But like, technically we should prove this, but we're just going to accept it as a lemma for right now. So then, here's my claim. The square root of 2 is irrational, right? So to prove this, what we'd want to do is show the opposite. So, and then get to something that is always false, right? We're not actually trying to get to something where we are proving it like through a direct proof. So what we're going to do is suppose to the contrary that the square root of 2 is rational. Now at this point, we don't have a whole lot to go with, right? Like I flipped it, but what's my next step, right? And it's going to be probably in something in that definition. So what does it mean to be rational? What it means to be rational is that we know that you can always represent yourself as one number divided by another number, and both of those numbers should be able to be reduced down to their lowest common denominator, right? In other words, that A and B do not have something that evenly divides both of them, right? You can get them to their simplest form. So you can represent, basically you can represent all rational numbers as a fraction. There we go. So then, to the contrary, right, we're going to assume that the square root of 2 is rational rather than irrational. If that's the case, there are integers a and b such that a divided by b is equal to the square root of 2, and a and b can be chosen so that the fraction a over b is in its lowest terms, right? They have no common factors. So if that's the case, we can say that a squared over b squared is equal to 2, right? We're just going to take the square of both sides, or square both sides, because, you know, nobody likes square roots. That would mean that a squared is equal to 2b squared, right? Just multiplying both sides by b squared. We're just doing basic algebra at this point, and we don't really need to talk about every single reason for why we're doing this. This is why we're in paragraph form. We're not doing the two-column proofs. So if a squared is equal to 2b squared, well, that's 2 times a number. We know that a squared is going to be even. If a squared is even, using that lemma we just talked about, we know that a is even. Hold that thought. A is even. Therefore, right, there's some sort of a equals 2k for some integer k, so that a squared equals 4k squared. Right? That's the definition of being even. You can write yourself in the form, you are equal to 2 times some integer, right? And so in this case we use k, so 2k for some integer, which means that a squared is equal to 4k squared. But now, if we go back to our, the a squared equals 2b squared, right? And we were to make it so, and basically divide both sides by 2, right? We would have b squared equals a squared divided by 2, right? Now, if I take that and I know that a squared is equal to 4k squared, then I can say, well, then a squared divided by 2 is equal to 2k squared, which means that b squared is equal to 2k squared, and in that case, b squared is even. And using that exact same lemma, we know that b must be even as well. So now we know that a is even and b is even. Okay, if we know those two things, we know that they cannot be in the lowest, that AB is not in its lowest terms, right? We've not simplified it enough. They have a factor in common. They have 2 in common, right? They're both even. And so therefore that cannot be the case, that the square root of 2 is rational. And so because we've proven that the square root of 2 cannot be rational, we've proven that the square root of 2 is irrational. That's a proof of contradiction, right? I take the negation and I show that that negation leads to some sort of contradiction and cannot be true. And that is it for our 3 forms of proofs. So this week is going to be a little bit different because we're actually going to do some proofs, but more details with that in Canvas. If you have any questions, feel free to send me a message in Canvas, and I will see you online this week.